Hello and welcome, everybody. So, I have been working on a new project recently, and that's why I haven't uploaded in a long time. And so this new project is going to be a complete microprocessor from the ground up, designed to actually run complex code with subroutines, and, you know, it's going to have good, like, a bunch of memory access, memory mapped I/O. You know, it's going to be very general purpose. And it's going to probably be on par with like a 6502 microprocessor in terms of how fast and the things it'll be able to do, plus it will be pipelined. So that already in itself will improve it over a 6502. Okay, so I just want to show you, some of you guys who are watching might be familiar with assembly code. And so to make assembly code, you kind of have to have a way of like mapping out instructions or defining instructions. So I mapped out some assembly instructions here. So I mapped out add, subtract, add with carry, NOR, AND, XOR, XNOR, compare. Then I have shift operations, which are logical shift left, logical shift right, arithmetic shift right. Then I have load store, which is like load byte unsigned, load byte signed, and load word, store word, and then I have a different store word. This is actually going to go away, this new one, because the way I have implemented it will allow me to do this one no problem without having to execute sudo ops. Then I have multiply and divide instructions. So for instance, I can multiply two registers, RS1 and RS2, and it will go to the ML and MH registers to multiply low and multiply high registers, because multiply results in extra data. You double the amount of data you get out, so you have to handle it. And then the same with divide, is you get twice the amount of data out because you have a remainder and a quotient. So you have to update the divide remainder and divide quotient registers. Then I have jumps, or my branches. So I have a jump, which is an unconditional branch. Branch not equal, branch greater than or equal to, branch equal to, branch less than or equal to, branch less than. And then I have relative jumps also, so I can say to go to a specific address, or I can say add to the PC an offset. And then I have jump and link register, or jump and link, and then jump and link register instructions. And yeah, the way these work is I can jump and link, jump relative and link, jump relative, or jump and link register, or jump relative and link register. So basically, I have. And then I have, of course, for both types of instructions, I have like the register format, and then I have the immediate format. So that's the left and right column. So like you can say jump and link, and then the address is contained in register 2, or you can jump and link, and then the immediate value is the address. And so like on the right and left is basically all what actually gets done, like in the computer. So like when you jump relative and link register, you're saying the RA gets the RD register that you've specified. So the contents in RD become the contents now in RA. And then your PC gets the PC plus the offset contained in register 2. Now if you look at the difference between that and just jump relative and link instead of jump relative and link, we'll look at, jump and link register instead of jump relative link. You can see that now we're not adding an offset, it's just the PC becomes that. Now if you look at jump relative and link, and we're not doing the register part, it's just jump relative and link, not jump relative and link register. You can see that the return address just gets the PC plus 1. So we're just saying the return address gets the next line of code that we're at. Whereas with the jump relative and link register, we're saying the return address is contained in a register that we specify. So, I mean, it's useful for subroutines and lookups and stuff like that. And so this is going to be a very powerful architecture. And then you can see the architecture is actually defined over here. So if we scroll up, we can see I have my ALU ops here, shift, load store, multiply, divide, branch, and jump and link register. The same format as these purple or pink, whatever, hot pink boxes. Okay, so that's why it's split up like that. And now you can see that there's a lot of instructions defined here. So like, I'm defining 2 instructions per one thing here. And I had some vector instructions, but I took them out because I didn't need them for what I wanted to do, and the way they were being implemented wasn't like super useful. It kind of is useful, but kind of not. And so, excuse me, I might I might implement those later again, but then I would have to redesign the ALU, and I don't feel like doing that. These were possible when I was building it in Minecraft, just because of the way the ALU is designed. It was just easy to split the carry. But when you're using a block adder, then I would have to use 2 4-bit adders, or 2 8-bit adders, or 4 4-bit adders, or something if I wanted to get all the vector ops the way I was doing it. So it just wasn't worth it. So anyway, yeah, so all these instructions get defined from the way I laid out my instruction over here. So at the top here, you can see that we have a 32-bit instruction, and the format for that is the top 6 bits here. So this is the most significant bit, M is most significant bit, and the AR is the least significant bit. And then MSB means most significant bit, and then LSB is least significant bit. Excuse me. I'm drinking some coffee. Gotta keep going. So we can see that the add instruction here has a bunch of arguments after it. The reason we know it's add is because the opcode is 0000 000 sorry. So the if you put values in these 5 bits, it's the destination register. So we have 31 destination registers that are possible. Not 32, because 0 is the 0 register, so you can't write to the address 0, and you can't. And when you read from address 0, it always outputs 0. So, actually, before I fully go on here, I guess I should show the register map. And this is the register map here. So it basically says this value here is the actual like binary value that you put in as an address. So it's 5 bits, but I just expressed it as a decimal number. So we can see 0 is called the 0 register, R0. So when you're writing an assembly, you would, to specify R0, you would type in R0, or 0 register, you would type in R0. Then I laid out some temporary registers, which don't get saved to the stack when you do a subroutine. Instead, the temporary registers get written over, and they assume that they're temporary. That's why they're called temporary. So we have 12 temporary registers, mapping from 1 to 12 like that, or 0 to 11. When you use them, like when you write them in assembly, you'd call it T0 or T1 or whatever, and you have up to 11. Then you have saved registers after that, which you have 9 of. And these numbers can change, and like I can switch the amount of temporaries and saved registers I have. That's not fully set in stone yet. But saved registers are, whenever you run a subroutine, they are pushed to the stack, and whenever you return from a subroutine, they are then popped from the stack. So these are assumed to be saved, and these are assumed to be saved by the callee. Then you have index X and index Y registers, which aren't saved by they're not saved registers. So if you call a subroutine and you need to save your indexes for whatever reason, then you need to push those to saved registers, or push them to RAM yourself as a stack. Then you have the multi, mult-low registers. That needs to be centered and brought to the center. Then you have the divide remainder and divide quotient. Then you have the frame pointer, the global pointer, stack pointer, and the return address. So, excuse me once again, sorry. The return address, what that does is it says, it's a special purpose register, an SPR, that says the address contained in this register is where the PC will go when you call it. So you can load the return address into the PC, and it's just a special purpose register that's meant to be easily loaded into the program counter. The stack pointer tells us where in the RAM the base of the stack is, and so we can offset from there to store our variables too. The global pointer tells us currently where we are in memory, like where the code is originating. Or no, not where the code is originating, sorry. Global pointer is like where our it's like it helps us map out the RAM, so we can separate portions of the RAM, and the frame pointer is where we are within that section of the RAM. So like if I Google frame pointer, we can see what it is. The frame pointer points to the start of the stack frame. There we go. Sorry. So it lays out where in the stack frame we are, and then the stack pointer from there is is where in the base of the stack There we go. So you can have multiple stacks in your, so if you have multiple subroutines that you're calling, you change where the frame pointer is for each one. And then the global pointer, let's look at that. So, it's global pointer registers point to the global area. So, like, if you need to use it, and you can't see why, but whatever, I still have it for a thing. Always load the value into the global pointer when destroying the stack. So, like, it's just like an extra pointer register you can use if you need to take advantage of it. And so, like, I'd rather have it and not need it than need it and not have it. So, those are all the pointer registers, and then, you know, index registers are for, like, iterables. So, like, you know, if you had, like, I and Z or I, J, and K, if you're iterating through some for loops or something like that, you can use at least 2 there defined for that, and then you would have to start using your temporaries for that. And yeah, so basically, so I showed now the registers there. So the format here for add would say add these 2 values together and write to there, or add this value and the value contained in the 8-bit immediate, which gets sign extended to being 16 bits. So you could say take that 16-bit value, even though the lower 8 bits are the only ones that contain data, and add it with that 16-bit number and store it there into that register. And you can basically do that for all of them, except for the compare. The compare doesn't have a write back register. Instead, it updates the compare registers, which are like they tell you greater than, equal to, less than, all that junk. So then you have shifting. Oh, and so I was going to say, like, so the add instruction can either do the immediate plus argument A to the destination, or argument A plus argument B to the destination. So that's why over here we have both the register format and the immediate format. And the immediate format takes the 8-bit signed integer format. Oh, that's a typo. Like that. So the X length tells us how big the immediate is and then what it gets extended to. So if it says signed, then we know it gets sign extended. If it says unsigned, then we know it doesn't get sign extended. Whoops. So that's just 5 bits of the lower 16. Like, so this, it's a 16-bit number, but just the 5 bits contain, the bottom 5 bits contain data, basically. Then X length 2 is 11-bit signed, so it gets sign extended, and then 16-bit unsigned integer. Like, obviously you can't sign something that's already its full word length because it contains the sign, so like it doesn't really matter if you put unsigned or signed. It's 16-bit, so it's the full word. Same with there, and same with there. That's what those ones use, and same with there. So you can see here, oops. You see here we have just 8 bits of immediate, but it gets sign extended. Here was those 5 bits that I was talking about earlier. So with the logical shift left, if you enter the address or the opcode of 8, it will know that you're doing logical shift left. And then basically it will then take, it'll store it into the destination. This, source 1 being shifted by the amount in source 2, or source 1 being shifted by the amount in the immediate there. And you have logical shift left, logical shift right, and arithmetic shift right. If you want to do an arithmetic shift left, then you can just mask the most significant bit and it back over when you're done with all your shifts if you wanted to. Then now, of course, you have the load byte unsigned, load byte signed, load word, and then store word. I'm also debating if I want to make it store a byte. We want to do that. I think I should, because it's byte address memory, so if you store a byte, it won't write the upper 8 bits of the byte to being a 0, of the word to being a 0. It'll just store the lower byte and leave whatever's above it. So I think that'd be a good idea, so I think I'm going to add that instruction there, which will then shift over all these things, but that's no big deal. So yeah, I might add a store byte instead of just one store instruction like that. And then we have our multiply divide. Well, oh yeah, and so the way the load store works, sorry, is if we're loading a value from RAM, then we can say that the value from RAM is going to be stored in this destination address, and the value we're loading is going to be this base value plus either this as an offset or the 11-bit signed integer as an offset. So you can say I'm either going to, and since it's signed, you can either add or subtract an offset like that. That's why it's important that it's signed. So if you put in -3 here, and you put in and this register contained the value 5, then you're going to say go to the address 5 plus -3, and then load that. Sorry, you're going to do it 5 plus -3 from the immediate, and then load that into that destination register. Or you can say the offset is contained in another register. So you can say take the value 5 plus whatever the offset is contained in this register that we're reading, and then store it into that register address. And you can do that for branch byte unsigned and byte signed and word. And then store is where it gets different. You can see the color changes because this is no longer a destination register, it's source 3. So the instruction set really only has 2 sources here. So that means source 3 means we need to have 3 reads on our register banks instead of just 2 reads. And what this will allow us to do is we can say, here's the value that we want to store is contained in source 3 or something like that, or maybe in source 1 or whatever it's contained in. And then I'm going to store it to the value contained in source 2 plus the offset of source 3. Or the value I want to store is stored at source 2 plus the offset contained in that immediate. So you need 3 sources for that instruction, not 2. And so that was tricky. It was up to me. I could either implement that as 3 instructions without having 3 sources. So if I had 2 sources, it would take 3 instructions. Or if I had 3 sources, it would take 1 instruction. So I decided, screw it, I'll just add an extra source to my register unit. And now that just takes 1 instruction. And then of course we have the load immediate instruction, which then takes the 16-bit value and stores it in a register. Okay, so now we have our multiply and divide. So if you enter the address 16, the opcode 16, depending if you have a 0 or 1 here for the immediate or the source, it'll then take that as a whole immediate value, or just know that this is a register value that goes to a register source, and it reads out from a register. So you can say multiply these 2 values in the register, multiply that value plus times that 16-bit raw data, or you can say multiply signed this number by this 16-bit raw data, or divide the same thing, or divide signed with that, or with whatever's in a register. And then the branch, so we have our condition table there, which says if it's true, it'll allow the branch to go through. So whatever code we're searching for in that condition table, which is 4 bits long, so we can have up to 16 different conditions that we search for. And then we can say if we're jumping relative or absolute. And then we can say if we're using an immediate or the source value for where we're jumping to. So we can say the PC gets this value, or the PC gets what's in it plus this value, or the same with this. PC gets this value, or the PC gets that value, or the value in it plus that value as an offset. And then the jump and link register, you can say we're doing jump and link or jump and link register. The only difference is jump and link implies that the return address is 31. Jump and link register implies that the return address is specified by the user. So it doesn't imply anything, I guess I should say. And then 0 or 1 for immediate or source, if that's either a 16-bit immediate or if it's just a 5-bit source there. And then absolute or relative to determine if it's being added or if the PC is just getting that value itself. And now with that, for instance, we can do things like this. We can say jump subroutine to some label, and then the code that actually gets executed when you do that, the assembler will convert that to store word, and then your saved register 0 goes there, saved register, sorry, that should be saved register 1, then you do saved register 2, and saved register 3, 4, etc. You'd save all of your saved registers to the stack by saying I'm saving to the stack pointer, and then the offset of 1, 2, 3, 4. But actually, since I'm byte addressing my memory, you'd actually have to say 0, then this would become 2, because it's a word, so we're storing 2 bytes. So now you have to offset everything like this. Sorry about the background noise. So you can see that we'd have to address it like this because we're storing 2 bytes and the memory is byte address. So we'd say store 1 byte. There's 2 bytes at 0, 2 bytes at 2, 2 bytes at 4, 2 bytes at 6, and 2 bytes at 8 because we're storing words. And then you do that for all of your saved variables, and then it would execute something called jump and link, and then it would jump and link to label. So when you run JSR is an assembly directive, which isn't actually an instruction defined in the instruction set. JSR executes all of these assembly codes here, and then the assembly line jump and link to the label that you want. So jump and link will then put the return address of where you are +1 into the PC, or it'll take the PC address +1 and put that into the return address, and then jump label. So an example of this is like this blue box here. Shoot. Control+. So this blue box says if you can imagine, like, this is code, like some line of code, some line of code, some line of code, and then there's some line of codes that, like, all these are different lines. So you're on like this line that says do stuff, so you're doing some stuff. Then it says jump subroutine Brezi. JSR Brezi, what that will do is it will say, alright, I'm jumping to the subroutine called Bresenhams, but before it jumps there, this is all the assembler you write for the assembler, but it will actually execute all of those things I was talking about below here when you do JSR. It'll do all the store words for you, and it'll just push all of your saved values to RAM. Then it executes the jump and link label. So back here in this code example, when you do JSR Brezi, it pushes all your things, and then it does jump and link to your label, so it jumps and links to Brezi, in this case, for Bresenhams. So then it was like, alright, so I have some example code, like it adds, or subs, ors, adds again, and then it says RTS, which is return to subroutine. Which now, return to subroutine is another assembly directive, which isn't exactly coded in the instruction set. What it does is it then, instead of storing all your words like that, it now loads your words kind of like this, where RST would then load word, and then your stack pointer, and then it would decrement the stack pointer or whatever. So you'd pop off from RAM in the reverse way. So the way this should actually be written would be like 8, like that, and then you do S7, 6, SP, you know, whatever was the inverse of the order that you did it here. You would do it backwards there. So return from subroutine would do all that, and then at the end it would jump to the return address. So it does an unconditional jump to the address contained in the return address register, which tells you where you want to go back. So this right here makes it very easy for the coder to not think about all that other stuff under the hood. It just makes it so that it's very powerful. So you can say, I'm doing some stuff, I want to call a subroutine, and then I want to, when I'm done running that subroutine, I need to come exactly back to where I was, but the next line of code. So instead of coming back to jump subroutine Brezi again, you want to come to that +1. And so this is going to allow for pretty powerful architecture. So now I will show you the architecture. Okay, so here is the instruction decoder. Basically, the instruction decoder works by taking the 32-bit instruction, and it takes the top 6 bits here and breaks them off, and the lower 26 bits and breaks them off. So the top 6 bits tell us what instruction we're running, and that comes into here, which is the decoder over here. So if we input 0, the decoder outputs add. If we input 1, it tells us subtract. So this here maps to all the values that we had for our instructions. And then over here, it comes into this multiplexer. So the address comes in here, the 6-bit number comes in here, and depending on what the address is, so if we put in 0 for the top 6 bits, it would say add, and then it would take these bottom 26 bits and pass it through to this right here. If we put a 1 in this line here, it will take these 26 bits and pass it through to that input. Because this is a demultiplexer, it takes one input to multiple outputs, but this one input is 26 bits wide. So it takes this 26 bits and splits it out to any one of these outputs here. And so since some of our instructions take the same format, we can just OR them together because those operands would be the same. So since those operands are the same, we can just OR those lines together, and then we know what instruction we're doing based on that. So if we're doing an ALU op, we know that the control lines for the ALU op will come from there. If we're doing a shift op, we know the shift op control lines will come from there. So these are the control lines that tell us how to actually set up the execution unit to do what we need to. And these are just basically the register and immediate values that we need to know where to load and write back to. So this tells us how to set up the ALU and the execution unit. And then this tells us how to get our reads and writes done. So you can see there's our shift ops, then load ops, then store, load immediate, multiply divide, branch, and then we have our jump and link register here. And then basically these little triangles here are tunnels. They're basically a wire that we can't see that leads from this label to its own label, corresponding label on the other side here. So it's like having ran a wire, but without all the messy wiring in between, which would make this very hard to look at. And the same is true for here. Those will go to their respective tunnels on the other side here to just be passed out to go to the other units that are going to be in the CPU. So you can see these are the instruction decoder, which tells us how to interpret this chart here so that we can generate all of these assembly lines, or all of those assembly instructions. So we can see now, like, the register unit. If I file, open in a new window, dual port registers, there we go. So we can see, these are actually tri-port registers, whoops, I named it wrong. The way the registers work is because of multiply high, multiply low, divide remainder, and divide quotient. Registers all need to be able to get their own data in parallel. They can do that there, and they also have their own clock for those, the multiply and divide clock right there. Then all the save, temp, index, and pointer registers, aka the STIP registers, get their own clock, and then we have one write address for those, and then, this is the address, or the data that's going to be saved into the save, temp, index, and pointer registers. So the STIP registers, that's the data input. Then this is the write address for what register it's being written to, and that's the clock to allow us to actually clock it in. So you can see we have since 3 sources: source 1 address, source 2 address, source 3 address, and then we have our output sources here. So if we input something in this address, the data in it will come out there. And you can see, so you have one output, and then you have a bunch of ways of reading it, depending if this is on or off. So if this is on, it'll then take that value and pass it through. And then we have that for all of our general purpose registers and index pointers and all that stuff. And then we have our 4 multiply high, multiply low, divide quotient, divide remainder registers. And so, for instance, if I wanted to run this, I could write some multiply low data, put some data in there like that. Like I say, then the source 1 address will be the multiply low register, which is address 24. Then I could say, maybe do address 1 and also make this like address 31. Okay, so now if I write that using the multiply divide clock there, oh, I didn't put anything in the multiply low. There we go. So if I write that, you can see that the 125 we wrote in the multiply low is read out here as 125 there as multiply low, because the register for multiply low is 25, or 24, sorry, and we wrote multiply, oh, I have to reverse those, sorry. Multiply high is 24, and multiply low is 25, so that's reversed. I wrote it wrong there, sorry. So you can see when we load multiply high, we get out the data there, and if we were to then make it multiply low by putting in the next one over, you can see that it's now the multiplied low data. Now if I also wrote like some general purpose data, so here's some like general purpose data, 9185, okay. If I write that to address 1, you will see that that will come out source 2, because source 2 has the address 1. If I clock it, you can see that comes out there. And now the other one I'm reading is address 31. So if I read address 31, and whatever I write to it will come out here. So I haven't written anything there yet, so let's get some new data. Okay, let's put in 31. And then if we clock it, boom, that data came out there. And then of course we can change where, like, we can make this this one also, and you can see now it loads the same copy twice because we're loading one onto 2 different buses. So basically this is giving us 2 different buses that we can read from, or 3 different buses that we can read from, and 5 different data sets that we can write. We can write 4 of these registers and 1 of these other STIP registers at the same time. So we can write 5 registers at once, and we can read 3 at once. So this is like a complex register unit that is able to work very well for my CPU. And of course there's a register map to keep me in check of how I built it. So you can see, like, that's where the source 1, source 2, source 3 bus comes from, and the destination bus. Those are the register addresses. So now, if I show you so here's the multiply divide unit. It's really easy. It has A and B inputs, and then it's the multiply unit above it and the divide unit below, and then it just creates those bits like that. And then if I open excuse me, the ALU is quite simple. It's not as hard as you'd build it if you were doing it in Minecraft. It's much easier because you're splitting it up into multiple units. So here we have an adder, subtractor, comparator, and NOR, XOR, and XNOR. And these are all 16-bit gates. So basically we can put in some data here, both of these inputs. So obviously B is now greater than A, and so we can say, if I was doing a compare instruction, I would input some data and I'd update the compare flags, and now it says branch less than because A is less than B, or B is greater than A. If I wanted to just add those values, I would pass the so if I wanted to just add, I would pass that value out. If I wanted to sub, I would do that, and NOR, XOR, XNOR, and get all those values out. The other thing I can do is I can say if I was doing if I was doing an add instruction here, when I do the add instruction, you also need to update the ALU flag. Now let's do something that creates like a carryout. So if I were to put in that and that, so now if I update the compare flags, or not, update the compare flags, that A is still less than B. But now if I update the ALU flag, you can see that now we have this carry out. So if I was running if the next instruction I was running was a add with carry, I would implement the add with carry like that. And then when I do the add, on the right back, we update the ALU flag like that. So here's the ALU. It's able to do all of that junk and compare, and also do our add with carry, which allows us to sub with borrow, because you can do add with carry, and then you can of course do 2's complement on the add. So you can subtract with borrow basically by adding with carry and 2's complementing. And then the last thing really, so then here is our byte addressable memory. So the one thing I need to do is make it so that you can, it gives an alert if you try to do read a non-aligned word. Right now it doesn't do that, it only gives an alert if you try to write a non-aligned word. So if I run this, if I take an address that is not odd, so it's an even address, aka the least significant bit is off. And I put in, the easiest thing to test would maybe be like F4, 4F, like that. So now I can tell the order, so if it's 4F or F4, I can tell which way things are stored. So if I want to write a byte into this even address, the right side is evens and the left side is odds. So I could then clock that byte in, and I could read that byte out there, or if I read the word, it would read the whole word like that, and it just sees the low 4F. If I was just reading the byte like that, it sees that. Okay. So I could also store that byte into the odd address, which then stores it into this one instead of that. So if I clock that, now I read the byte. I'm reading the byte. Well, I have to adjust this. I have to adjust the reads on this. I should be reading the byte from this and should be placing it through the low 4 bits here. So that's wrong. And then the other thing is now it doesn't throw an error either when I read the word here, even though it should, because the word is not aligned because the address isn't on a 0. So there's a few things to fix still in this. Now the other thing is, now if I try writing a word, the moment I try writing a word, but the least significant bit is on, it instantly throws this word not aligned, and it prevents me from storing. So it won't, like if you accidentally clocked it, it won't store over what's in there. It won't store zeros over what's in there. It just won't allow you to store at all. And so the word, because the word isn't aligned on the 0 boundary, if you're storing 16 bits, aka 2 bytes, you have to store it at the 0 boundary so that it goes from the even side here to the odd side here, and you can write a full 16-bit value like that, because it's all done on the least significant bit. So now if I was trying to write a word to a 0 aligned boundary like that, now it says word is aligned basically, and now it stores to both, not just one or the other, and it stores the data here. So now, instead of it saying, if we were to read the word here, it would say 4F, 4F. Now if we were to write that data, it would say F4, 4F. So if we clock it, now we wrote the whole word, where before we wrote the same byte to the low and the high end. So I just have to work on the read system on this, and then it'll be done. And then the idea here is you're going to be able to have all these inputs, or all of these gates. So over here will be the instruction decoder. Then, well, so like actually over here will be the instruction decoder. Then you have the all the control lines coming through. Then you have the register unit here, with the control lines passing through to the ALU, shifter, and multiply divide unit. And then all that stuff passes through to the RAM, and then some of the control lines loop back around. So it'll look like oops. It'll look something like, yeah, like this, where you can have all these stages separated, and then you can easily pipeline them by putting registers in between each one, and then all your control lines will be easy to put into the register that passes through. Anything moving backwards doesn't go into the register. Anything moving forward does. So this line here doesn't come through the registers again. That wouldn't make sense. So anything coming back around is not. And you can see, like, my CPU is very based on MIPS. So MIPS and RISC-V. So like here's a good example. It's going to be very similar to this. And then you can then do all of your pipelining, and you can do your forwarding and stuff like that. And it'll be pretty nice to have a very high-end CPU running. And sorry if this video is longer than normal. I just wanted to show you guys what I've been up to recently and why I've been gone. This video... Okay, so the other thing I want to reveal is I'm going to be giving away 5 copies of Logic World when the game releases in February. I haven't been given an exact date, release date for the game yet, so I don't know when in February it releases. So when I do get an exact confirmed date, I will be releasing a video stating that the giveaway is starting, and then it'll be done through Gleam so that there will be multiple ways to enter, and then to improve your chances of winning. And then also it would help me out by sharing my channel and all that other junk that goes along with it. So, wow, sorry for the dogs. Hopefully we find out soon. I'll put out that video, and then since I'll be building the CPU in Logic World and I'll be posting videos of that, you guys will be following along and be able to build the same CPU or download my components or my boards as I go and be able to actually use this architecture. The other thing that's happening is that I'm writing an assembler for this, so you're not going to have to be writing in machine code. You're literally going to be assembling the instructions that I have defined in my instruction set here by typing in these exact instructions. So this is a representation at which the assembler will interpret them. The assembler will also have a linker, so you don't have to say jump to address 5. You can say jump to location dog, and dog maps to like 5, you know. So you as a human don't have to keep track of where you are in the code. But when it gets assembled, it will convert all down to just being an exact location. This will make it very easy for you in the assembler. There'll be things like there'll be equate instructions, so you can say dog equates to 5. Once again, sorry for the barking. So dog equates to 5, which basically says every time you use dog, it's actually putting in the value 5. Then you can say origin, which is like the origin of your code, which tells you where in the RAM it's going to get assembled or whatever. Now, in my case, since it's a microprocessor, it's really where in the program ROM it's going to be assembled, but whatever. Then you have define byte and define word, which literally write into RAM the byte or the word that you're defining. And you can store that as like so you can say me, or you know, so you can say like define byte me as 1300 or something like that. And so it'll say the location called me in RAM gets 1300. And so you never have to worry about the actual location. You can just say, load word from RAM, and then you could load word me. You know, you can load that immediate value, and it will load. You say the register. So if you want to save that into a saved register, and you do that, it would literally take the value. It'll say, okay, I know where in RAM me is mapped to. And it'll take that address, me is actually an address, and it'll say load that address into save register 5. So since me is an address of RAM that contains 1300, it'll take 1300 and load that into register saved 5 or save register 5. So you can do stuff like that. You can also store ASCII tables and stuff like that. And so that's why I was doing everything as byte address memory, so that you can have ASCII characters and have one ASCII character per memory address. Make it pretty dense like that if you're doing ASCII codes. So displaying to screens and stuff like that should be pretty easy. And yeah, since it's all memory mapped I/O, if I don't use all 64K of RAM, if I only use 32K, then I have 32K left over of I/O if I wanted, you know. So I'll figure out the RAM memory map later. So far I've just got the register memory map defined. But the RAM memory map will probably be based pretty similar to the HCS12 microarchitecture because I'm most familiar with that memory map for the RAM. But yeah, now that I'm done talking and rambling, I hope you guys have a great day, and if you're interested in this video, please share it with your friends and help me grow my channel, because I may not be able to upload videos every single day, but I am uploading quality videos in my opinion. They may not be the most highly produced, but they're quality content nonetheless, in my opinion. And if you have any suggestions or comments, just leave them below. I'll check them, I'll comment them, I'll probably pin them and heart them too. Just trying to help grow this community, and don't be afraid to share any of this to Reddit either if you guys find it interesting. So thanks for watching, and hopefully I'll see you guys in the next time when I start building some more of the components. Peace.